Hello everyone and welcome to another class. This is a short tutorial video on empirical formulas, molecular formulas, percentage by mass calculations. So what exactly is an empirical formula? Usually in chemistry, when we say empirical formula, we are simply looking at the smallest whole number ratio distribution of atoms in a compound. Okay, so we know that for every compound there is a formula for that compound, and oftentimes the formula we always know is the molecular formula. So very soon we'll also be talking about what a molecular formula is. But usually what is written commonly, or what we often encounter, is the molecular formula. Is the molecular formula. So we are saying that the empirical formula we are looking at the smallest whole number ratio distribution of atoms in a compound. Okay, so we are looking at the smallest whole number distribution of atoms in the compound. Okay, let me just increase my font. So, smallest whole number ratio distribution. So that is empirical formula. Now, molecular formula is simply the total distribution of atoms in the compound. Okay, so the total distribution of atoms in the compound, that's what makes up the molecular formula. So when we write a formula like maybe say CO2, okay, CO2 is the molecular formula for the compound, but CO2 also is the empirical formula for it, because there is no simpler formula that can, other than this, that can describe the smallest whole number distribution of atoms in the compound. So for this, it is both an empirical and the same is also a molecular. Okay, so maybe for a compound like let's say butane. Okay, so usually for alkanes, CnH2n plus 2. Okay, so if it's butane, that's 4 atoms. So when n is 4, you're going to have C4. 2 times 4 is 8. 8 plus 2 is 10. So C4H10. Okay, so for a compound like butane, which is C4H10, if we want the empirical formula and we want the smallest whole number ratio of it, we are going to use a number that can divide both the 4 and then the 10, okay, such that we are going to be left with numbers that cannot be divided further again to give us whole numbers. So on a quick look, we can see that 2 would be a good factor to use for our division over here. So 2 goes into 4 twice, so we are going to have C2. Then 2 goes into 10 5 times, so C2H5. Okay, so that's going to be the empirical formula for butane. Okay, now when you have the empirical formula and you want to move to the molecular formula, it's simply a multiplication of the formula you have as the empirical formula by the factor for which you use to divide. So in this case, we used 2 for our division. Okay, so when we want to get the whole number, or when we want to get the molecular formula, sorry, we are just going to multiply it by 2, and then we get back our C4 and then our H10. So that's just basically a brief overview of what we are going to be doing. But to establish our understanding, we have to look at some questions. But before that, let's look at percentage by mass calculations. Okay, so usually in a compound, okay, we realize that a compound is made up of 2 or more elements that have been chemically combined. Okay, so as part of the work chemists do, they always want to know how much of what element is involved in the formation of a particular compound or any compound. So for instance, let me use CO2, this CO2 that we have here. So with CO2, okay, realize that in CO2 we have carbon, we have oxygen, right? Carbon has a relative atomic mass of 12. That of oxygen is 16, right? So if you want to find the percentage by mass of this, maybe say carbon in carbon dioxide, first of all we need to get the molecular mass of the compound we are dealing with. And with the molecular mass, we are simply looking at the sum of the individual relative atomic masses. So for this, we have carbon being 12 plus oxygen being 16. And since we have two of it, 2 molecules of oxygen, we are going to just multiply that by 2. And when we are done, you realize that we are going to have, this becomes 12 plus 32, which is 44 grams per mole. Okay, so grams per mole. So if you want to find the mass of the percentage by mass for carbon, that is going to be 12 over 44 multiplied by 100. So percentage by mass. So with this we can divide. 2 goes here, or let me say 4. 4 goes here 3. 4 goes here 11. And then we have 300 on 11. And on the calculator, that will give us 300 on 11. Just punching it in my calculator. 300 divided by 11. So that's giving us 27.27. So 27.27%. So you can just make it 27.3%. Okay. So that's the percentage by mass of carbon in carbon dioxide. Obviously, if you want to find that of oxygen, there are two ways. You can either go by the same route. So this time around it's going to be 32 over 44. 32 over 44 times 100. Or you simply subtract this 27.3. This 27.3 from the 100%, and then what you'll be left with is that of oxygen. So when we do that, you realize that you have 72.7. Okay. So basically that's just a brief overview of the percentage by mass calculations, etc. So let's see whether we can do some questions together. Let's see whether we can solve some questions together. Let's look at some questions together. So sorry about this. Just a moment. So we're all interested in the question. Okay, let's just solve the question and then check if our answers are correct. So it says that find the percentage by mass of each element present in C6H5NO2. Okay, C6H5NO2. And we've been given the relative molecular mass to be 123.12. Okay, so percentage by mass of each of the contents for C6H5NO2. C6H5NO2. Okay, C6H5NO2. So since we have quite a lot to cover, I'll just do for, let's say, 2 of them. Now we're given the total to be, the relative molecular mass to be 123.12. So you have carbon, which is 6 atoms of carbon. That's going to give you 12 times 6. Okay. Adding with hydrogen is 1 times 5. Nitrogen is 14. Then plus oxygen is 16 times 2, which is 32. So when you add that, 12 times 6 is 72. So you have 72 plus 5. 72 plus 5 plus 14 plus 32. So yes, that gives you 1, 2, 3. So they are right. Okay. Now if we want to find the percentage by mass for that of carbon, we are going to multiply the relative atomic mass of carbon by the number of atoms of carbon, and we are going to divide it by the total mass. That's the molecular mass or the molar mass of the compound. And then we multiply it by 100. Okay, so we're going to have 12 times. So we are going to have 72. We are going to have 72 plus 72 divided by 123. Okay, when you solve for this, you are going to get 72 divided by 123.12. So I'm going to have about 58.5%. Okay, so this 58.479. So let's say 58.5% or 58.48, 58.5. Okay, and then you repeat the same process for the rest of them, and then you get their individual components. By the time you are done, the sum of it should give you 100%, because when we say percentage by mass, we are simply referring that mass to 100 grams of whatever compound we are dealing with. So if we took 100 grams of C6H5NO2, the mass of carbon in it alone is going to be 58.5 grams. That's what we mean by percentage by mass calculations. So we want to continue, and now we want to take some. Let's see another question. Okay, let's see. So there is another question here. Calculate the mass of oxygen in 2.20 grams of carbon dioxide. Okay, calculate the mass of oxygen. Calculate the mass of oxygen in 2.20 grams of CO2. Okay, so what can you do with regards to this question? What can you do? First of all, let's do what we already know. Okay, calculate the mass of oxygen in 2.20 grams of carbon dioxide. We have been looking at carbon dioxide for some time now. We know that the molar mass of carbon dioxide is going to be 12 plus what? 32, which is 44, okay, grams per mole. Now the mass of carbon in that is 12 on 44, or as a fraction is 12 on 44, and that for oxygen is 32 on 44. Okay, so this is by far what we know. So how can we relate this to that of 2.20 grams? So it means that we have a sample of carbon dioxide, and the mass of the carbon dioxide we have is 2.20 grams. But what we have, or what we have fine details of, is that of um 1 mole of carbon dioxide. Okay, so we are just going to bring it into perspective, and how we are going to do that is to simply multiply it by this mass. Okay, so we are going to multiply this 32 on 44, which is an expression of the fractional mass of oxygen in carbon dioxide as a compound, and then we are going to multiply it by this 2.20, and that is going to give us the mass of oxygen in this sample. Okay, so when you calculate that, you are going to get we're going to get 1.6 grams. Okay, so this is going to give 1.60 grams. Okay, 1.60 grams of oxygen. Okay, so let's take a look at one last question under percentage mass calculations or fractional mass calculations. So it says, what mass of HNO3 contains 2 grams of oxygen? What mass of HNO3 contains 2 grams of oxygen? Okay, so let's go back. Let me clear this page. Yes, so what mass of HNO3 contains 2 grams of oxygen? So we are going to do the same thing we did with the previous question. We are going to start with what we know. Okay, so this is a little bit of a twist from the previous question, in the sense that in the previous one we were given the total mass. Okay, we're supposed to just find the mass of carbon dioxide, sorry, the mass of oxygen in that unknown mass. But in this case, we've been given the mass of oxygen in an unknown mass that we have to find. Okay, but we are still going to use the same pattern. Okay, so since they are talking about oxygen, let's do that for oxygen. The total mass of this, the molar mass of HNO3 is going to be, we have HN3, so we have 1 plus 14 for nitrogen plus 16 times 3 for oxygen, because it has 3 in that compound. So the total, we have 15 plus 48. Okay, and then 15 plus 48 is 63. Okay, so 63 grams per mole. Okay, now what else will we do? From this we can see that the fraction or the mass or the fractional mass for oxygen in this compound is going to be 48 on 63. Okay, So what else can we do now? What else can we do now? So this is what we will do. Now, if we were to express this as a percentage, okay, if we were to express this as a percentage, so multiply by 100, what that is going to give us is going to be 48 divided by 63 and multiplied by 100. It's going to be 76.19. Okay, 76.1904. Okay, so what we are saying is that if we took 100 grams of HNO3, 76% of it is going to be made up of oxygen. Okay, so we can just write a simple ratio and proportion for it, okay, to get that with respect to the 2 grams. So I'm just going to clean this side. Okay, so we are going to say that 76.19 grams of oxygen is in 100 grams of HNO3. Okay, so when we have 2 grams over here of oxygen, in what mass of HNO3 is it going to be in? Okay, and by ratio we know that it's going to be 2 on 76.19 times 100. When we do that, let's see what we are going to get. 2 divided by 76.19 times 100. So you're going to get 2.625. Okay, so this is going to give us 2.625. Okay, or 2.63 grams. So that's about that. There are other ways you can do this. I think this method is quite easy to follow. Okay, so let's try one question on empirical formula, and then we would bring the class to a close. I think 30 minutes for a video is okay, for a tutorial is okay. So last question, where is that question? Okay, so we started with this question, or I started, but so unfortunately it wasn't recording, so let's go over it again. So this was the last question I was talking about. The experimental setup shown in the figure can be used to determine the empirical formula of copper oxide. The following experimental results were obtained. mass of the empty dish in grams, 24.58. Mass of dish plus copper oxide in grams, 30.12. Mass of the dish plus copper at the end of the experiments in grams, 29. Now we are being told to calculate the empirical formula of copper oxide and write an equation for the reaction. So this is the setup. This is a reduction reaction. So copper oxide being reacted with hydrogen under heat is going to produce copper. Oxygen will escape. Okay, so hydrogen is being used to reduce copper oxide into copper. So it's a redox reaction or a reduction reaction. We are not talking about redox reactions now, so I think that would be about that. But if you know anything about redox reactions, you know that addition of hydrogen signifies reduction. So that's just by the way. Now, with regards to what we are supposed to be doing, how are we going to go about it? We first of all have to take note of the masses that have been given us. We know that copper oxide is a compound going to be made up of copper and oxygen. So these are just the relative atomic masses of the elements, copper and then oxygen. So for copper, 63.5, for oxygen, 16. So with that, how do we go about our work? Now, we've been given the mass of the empty dish and then the mass of the dish plus copper oxide. So we can quickly find the mass of copper oxide by doing a subtraction between these two. Okay, this and this. When we do that subtraction, what we are going to get is going to be the mass of copper oxide. So we are finding the mass of copper oxide from here, 30.12 minus 24.58, and we come up with 5.54 grams. And then, so we have the mass of copper oxide. Now, based on that mass, how do we get the other components? So let's go to the next page. We have to find the mass of oxygen. Okay, now remember we said that the mass of, in the reaction, oxygen is going to escape. Okay, but since we have the mass of copper oxide, we can always find the mass of oxygen. Okay, especially when we have been given this important information. Okay, this information is very, very important. Okay, this information is very, very important. So we are being told that the mass of the dish and copper at the end of the experiment. Remember, at the end of the experiment, your oxygen would have escaped, so you'll be left with only copper. So with this mass, we can find out how much oxygen escaped. Okay, so when we do a simple subtraction between the mass of the dish plus copper oxide and then the mass of the dish plus copper at the end of the experiment, okay, what we get, which is 1.12, okay, 1.12 grams. That's going to be our mass of oxygen that escaped. Okay, so with that information, okay, so we see the mass of, we do the subtraction again. So this is our mass of oxygen. Now, if you want to find the mass of copper, it's simple. We just have to take out the mass of oxygen and then we are good to go. Okay, so we take out the mass of oxygen. What you are left with is the mass of copper, so which is 4.42 grams. Now, we are done with the word problem aspect. What we are left with is just calculations with regards to empirical and molecular formulas. So first of all, we are just going to find out the moles of copper and then the moles of oxygen in the compound copper oxide. And we are going to use the given masses and then the molar masses to do that. So that's why we have 4.42 grams for copper divided by 63.55, which is the molar mass of copper. And respectively, we do the same for oxygen. And that will give us the number of moles in each of the number of moles of each of the elements. So when you do that, you realize that you get 0.06955 for copper and 0.07 for oxygen. Then you go on by dividing to get the actual whole number ratio. You divide by the least moles. When you make a careful comparison, you realize that 0.069 is less than 0.07. So we divide through by 0.06955 moles on each side. And we are left with 1 for copper and 1.006 for oxygen. So in conclusion, you realize that the empirical formula is a 1-to-1 ratio. So this is a CuO. So that's just by the way, okay? So that brings us to the end of this tutorial. Don't forget to share, to subscribe, to like, and send us your comments. Until another time, have a wonderful day. Bye bye.